All right, so now that we've introduced parametrized curves, we're going to talk a little bit about derivatives, taking derivatives of parametrized curves, and how to best interpret them. And what we'll see is that this is tied really closely to the velocity and the speed of the parameterization. So first of all, a definition for taking the derivative of a curve. We have our parametrized curve. This is x of t, and as a reminder, there were two components. There's the x component and the y component, both functions of our parameter t. We can say that such a curve is differentiable if both x of t and y of t are themselves differentiable. So specifically, if this function and this function are both differentiable. So x prime of t and y prime of t are both well defined. And if that's the case, we say that our parametrized curve is differentiable, and we denote the derivative of the parametrized curve as x prime of t, right, where this x is the vector x. And that will just be used to denote the derivative of each component. So as a very quick example, right, if we take our favorite parametrized curve from last time, this is the parametrized curve denoting the unit circle, cosine of t comma sine of t, then the derivative of this parametrized curve, we would take the derivative of cosine, gives us negative sine, the derivative of sine gives us cosine, so we would get this as our derivative. And I just want to point out that this is in fact, the derivative is going to be another vector valued function, right? Because it has a single input t, and it has two outputs, right? This component and this component. So it's a vector valued function, and in particular, it is itself a parametrized curve, right? So to see this explicitly, remember that x of t, our unit circle, was traced out so that it started at the point 1, 0, and then it went counterclockwise like this, right? So to being traced out in that direction. Well, x prime of t is this expression negative sine of t comma cosine of t, and we can see what this will trace out. And it turns out this will also trace out the unit circle, just in a slightly different way. So at time 0, we'll be starting at negative sine of 0 comma cosine of 0. So that's negative 0 comma 1. We're starting up here. Let me actually choose a different color here. So we start up here, and then we go to trace out this curve, and we'll see that this also goes counterclockwise. It also traces out the unit circle. It just happens to start at this different location. So the derivative of x of t is this new parametrized curve, x prime of t. But it turns out that we really, more often than not, do not want to interpret x prime as its own parametrized curve, right? It turns out we'll want to interpret this in a slightly different, slightly more geometric way. So let's see, what does x prime of t represent geometrically? Well, formally, x prime at a given time t naught, we said that this was equal to nothing more than x prime of t naught comma y prime of t naught. But remember, going back to our original Calc 1 definition of the derivative is a limit expression, right? So x prime of t naught is really the limit as t goes to t naught of this difference quotient, x of t minus x of t naught over t minus t naught. And then the same thing is true for the derivative of y. So this formally represents these two limits, which we can then break up in the following way. First, I can pull this limit as t goes to t naught. I can pull that out to the front. This division, divided by t minus t naught, that turns out to be just dividing by a scalar. And so by our rules of vector and scalar multiplication, I can pull that common component out of the vector. So I can pull that out here. And then finally, this x of t minus x of t naught, comma y of t minus y of t naught, well, I can break that up using my rules of vector addition. And so to be just a little bit more careful about this piece, whoops, wrong thing there. Just want to separate this for a second. right? As a reminder, with vector addition, I can take two different vectors and add them together to get a single vector. Similarly, I can take a single vector and, assuming I follow proper algebra rules, break this up into two distinct vectors, right? Using the same rules of vector addition. And so what we see here is that, in fact, this entire piece, right, or rather, this entire thing is a vector. While down here, I've broken this up into vector addition, or in this case, vector subtraction. So this is a vector, and this is a vector, right? And so what I have down here is really a displacement vector showing the displacement between the point x of t, y of t, and x of t naught, y of t naught, and then multiplied out front by this scalar piece right here. So what does this really represent? Right? Well, we just said that, I guess this is that same expression up here. And I want to see what this looks like geometrically. So here's a schematic picture of our parametrized curve denoting the unit circle. I'm going to mark off a given point t naught. Let's just say maybe this is t naught. And let's say, for example, that that corresponds to this point right here. So that's x of t naught over here. And similarly, I can choose other points, other t values, to construct this displacement vector. So this is the point x of t naught, denoted by this point right here. And similarly, I can take and calculate an x of t for a given t value. So let's say t is right here, right? And let's say that corresponds to this point right here. So this is x of t naught, this is x of t, and then the expression up here before the limit, so this expression, is found to be the displacement vector x of t minus x of t naught. So that's the vector that is pointing in this direction. Right? And then when I multiply by this scalar, 1 divided by t minus t naught, that will expand, right? That'll stretch by a certain factor this vector. So maybe we no longer get that vector, but instead we get this vector right here, right? Because we've stretched it by this given scalar factor. Okay, and so that's true for this given t. And what we want to do is now take a limit as t goes to t naught, right? As t gets closer and closer and closer to t naught. So if we choose a different t value, right? And let me see what's the best way to do this. Let me erase that and erase this. All right, so if I choose a slightly closer t value, let's say a t value that's very, very close, then I would get a point here that's very, very close. But similarly, I would get a displacement vector. And then that displacement vector will be scaled by this factor t minus t naught, or 1 over t minus t naught. So I'd end up with perhaps this as my vector. And so if I construct a limit of these, right, as my t values get closer and closer and closer to t naught, then these expressions that I get will get closer and closer and closer to the limiting value they get, which will actually be a tangent vector of a certain length at the point t naught. All right, so this expression, this x prime, capital X prime, is really going to give us a vector that is a tangent vector to the curve at the original point. And this will be called our velocity vector. So we can summarize this as follows, right? X prime of t naught will actually give us the velocity vector to the curve x of t at the time t naught. This velocity vector will always be tangent to the original curve, and its length, right, because we keep scaling it up by this extra factor, it turns out that its length will be, as a reminder, length is denoted like this, and is, let's see, right? This is equal to the square root of x prime of t naught dotted with x prime of t naught, right? Because that length is just going to be the square root of that vector dot itself. That length will actually be equal to the speed at that given time, right? The speed of the parameterization, showing at the speed at which we are tracing out this curve. All right, so let's see an example of this, right? We'll go back to our old friend, the unit circle, being traced out using this parameterization. What we've seen is that the derivative of x of t will be x prime of t, which is the derivative of cosine is negative sine. The derivative of sine is positive cosine. So this will be our velocity vector. And the speed of our parameterization, right, just sort of walking through this, this will be the square root of this vector dotted with itself. So that will be, negative sine times negative sine plus cosine times cosine. That's just sine squared plus cosine squared, which our Pythagorean identity says is just equal to 1. So this curve is being traced out at a uniform speed. The speed is just equal to 1. So it's traced out at speed 1. Furthermore, we have a new interpretation of our x of t versus x prime of t picture from before, right? So recall, our x of t, unit circle, starts here on the x-axis, gets traced out in a positive direction. X prime of t we saw started up here on the y-axis and gets traced out. But what we can see now is that this curve is better interpreted as a velocity vector. And to see this, look at the initial moment in time, right? The initial moment in time, our x of t started here, our x prime of t started here. It's maybe more geometrically intuitive for me to think of this not as a point in xy space, but as this arrow, right? The arrow right here. And if I transplant that arrow up to this picture, what I get is the velocity vector of my parametrized curve at that given moment in time. If I were to choose a different point in time, like let's say my point in time is pi over 2, right? Well, at time pi over 2, x of t, at time pi over 2, x of t is going to be right up here, and x prime of t is going to be right here. But again, x prime of t is better interpreted as this arrow, which transplanted up here means that at that moment in time, my velocity is going in this direction, right? My parametrized curve is being traced out in that direction. Perfect. I want to end just by going through a perhaps sort of illustrative example to see what will happen if we reparameterize this curve sort of in the way we've already seen. So specifically, what would happen if instead of having our original x of t be cosine of t sine of t, it was equal to cosine of 2t sine of 2t. And I'm going to do the lazy professor thing where I just try to draw in 2's here in a different color. And let's see how having that extra 2 in there percolates throughout the problem. Right? So this is a reparameterization of x of t. It traces out the same locus, that unit circle. And yet, the derivative of x of t, so x prime, will require the chain rule. So the derivative of cosine of 2t is going to be negative sine of 2t times the derivative of 2t, so times an extra 2, which I'll put out front. And similarly, the derivative of sine of 2t is going to be cosine of 2t times the derivative of 2t. So we end up with this extra factor out there, this extra factor of a 2, which pictorially will mean that x prime of t in green will be a circle of radius 2. So we'll end up with a bigger circle here. And when I'm drawing my corresponding arrows up here, each of those arrows will be bigger as well. right? And how much bigger will that be? Well, to compute the speed, we just compute the square root of x prime dot x prime. We'll end up with these extra factors of 2 everywhere, which I'll draw in quickly. Right? There are extra factors of 2 in here, but on the outside there's a 2 and a 2, so we end up with a 4 and a 4. And so 4 sine squared plus 4 cosine squared is just 4. And so our new speed is the square root of 4, which is just 2. Right? And so what we see is that, in fact, this reparameterization really does trace out the same curve, the same locus. Right? It's still the unit circle. It just does it at twice the speed. And indeed, these velocity vectors have doubled in size. So that's it for this time. I'll see you next time.